In this video, I'm going to give you a way I like to think about vectors as far as them being linearly independent of what they span and their bases. And I like to think of them as like colors. This is paints. So the wave idea of a color is probably more accurate for vectors, but I like to think of paints because it's very concrete. So maybe some oil or acrylic paints that you pour out onto a palette. So the idea are the vectors then are your paint colors. The vector addition is when you mix paints to make new ones. And then the scalar multiplication is like when you're mixing your vectors together, you adjust the proportion of paint. So like 2 red plus 1 yellow will give you kind of a dark orange, and you have twice as much red paint. Did I say 2 red? Yeah, you have twice as much red as you do yellow. With paints as an analogy now, when you talk about an independent set of paints, that means you cannot duplicate one of your colors by mixing the other colors in your set. So like red, yellow, and blue, if you have those 3 colors, red, yellow, and blue, there's no way you're going to mix yellow and blue and get red. Similarly, there's no way you're going to mix red and blue to get yellow, and finally, there's no way you're going to get mix red and yellow to get blue. So those 3 colors are independent. If you had a dependent set of colors, you can make one of your colors by mixing some of the other paints in your set. So if my set was red, yellow, orange, well, I can make the orange from my red and yellow. So orange is dependent on red and yellow. And theoretically, if somehow you had paint mixed together and you could extract out one of the colors exactly, theoretically then red could be made from yellow and orange because you would extract out the yellow from the orange. I mean, I guess you can't really do that with this set of paint, but let's pretend we have some magic. But you can see how orange minus the yellow will give you back your red. Then span becomes a description of the colors you can make. So if you have red, yellow, and blue, from what I understand from color theory, you really can make all the colors. If you have red and yellow, you can get a bunch of shades of orange and red and yellow. And then finally, a basis is the smallest set of paints that will allow you to get all the colors. So here, red, yellow, and blue would perform the function of being a basis because you can theoretically get all the colors by mixing those 3 colors together. There's another system, another basis. That would be cyan, magenta, and yellow. And I believe those will allow you to get all the colors as well. And you'll notice they both have 3 vectors in them. So in that case, the dimension of our color space will be 3. I should also say that I did jump right into talking about linear independence, span, and bases, and I really should have thought a little bit harder. Are these colors really a set of vectors? Do they conform to the vector space laws? Well, as I already mentioned, you do have to have that subtract, which is a bit fanciful to think you could remove the red or the yellow paint from the orange, but let's just pretend because we would need the subtraction. Also, you would need an identity vector, so you would need some paint that could mix in with others and you would still preserve the color. So I don't think white does it, or at least in not my mind. So you would have to have some identity color. I don't know what that would be, or if that's even realistic in the way vector subtraction isn't quite realistic. But all the distributive laws and things, those hold up pretty well if you just kind of go mentally. It doesn't matter if you mix red and then yellow versus yellow and then red. So a lot of those other algebraic laws hold quite nicely. And as I said, if you don't think of these as physical paints like some acrylics or something, but you think of a waveform, then everything becomes just right. And as far as that painting analogy goes, so the bases, those are the painters who want to have this tiny little set of paints, but still have the broadest range of things. They still want to be able to paint everything. So what they're looking for is a basis of paint. But you can also see how the ideas of linear dependence and independence, in other words, what paints or what colors you can and cannot make from your set, as well as the idea of span. Again, that's the idea of what you can make. And then bases, what's the most kind of small set you can actually live with but still make everything? Those are all important questions. One other visualization I wanted to show you is what the span of two vectors look like. So here I have two vectors in R2. This is the same for two vectors in R3 or R4 or whatever dimension. We had talked about when you add two vectors, you have that parallelogram that you make. That's the parallelogram we make when we move the start of this vector to the tail of this vector, like so. And then we do that with this other vector too. We take the start of this vector, move it to the tail of our other vector. So we get this parallelogram. This point at the tip where they both meet, that's going to be the sum of the two vectors. Before I continue, I should say that the span of v1, v2 are all linear combinations of v1 and v2. That is, all vectors of the form a1 times v1 plus a2 times v2, when a1 and v2 are simply scalars. So far what we've had is v1 plus v2, so a1 and a2 are equal to 1. And when we add them together, we got this one blue point here. Now let's say we scale our v1 vector by something smaller than 1. So let's say we have 1/2 of v1, and we want to add that to v2. I'm going to move my vectors for my vector addition, and I'm going to get this point here. And then if we multiplied a1 by something even smaller than 1/2, let's say we multiplied it by 0, we would just get v2. Now let's say we multiply v1 by something negative, such as -1. So it's the same vector as v1, but in the opposite direction. So now when we do our vector addition, we're going to get this point over here. If we had multiplied by 1/2 v1, if we were here, we would have gotten this point in between. So essentially, adding some scalar multiple of v1 to v2 is going to give us the line in the direction of v1 that passes through the point v2. Similarly, adding v1 plus a2 v2 is going to give us the line in the direction of v2, which is the straight up and down line, that passes through the point v1. Now let's see if we scale v1 by something smaller than 1, so we have a fraction of v1. Also v2, we'll scale it with something smaller than 1. So when we add our two vectors together, oops, need to move this one first, they get stuck. We're essentially going to have something in the interior of kind of this area here that's defined by our two vectors. I've kept v2 scaled by something smaller than 1, but I scaled v1 by something larger than 1. In particular, it looks like I tried to scale it by 2. So now, and remember, it's not v1 we're going to, it's v2, so way over here. And now I'm going to get this point over here. So it's still sort of in this arc, if we extend this arc sum, right? Here, this point was interior still to the parallelogram. This one is further out because we're sort of extending the parallelogram to something that is this long. Now I'm going to keep v1 extended as twice as long. I'm going to extend v1 now greater than 1. So now what I get is this parallelogram, and I have something over here. And you can add more points scaling as long as you're scaling them both by positive. What you'll eventually end up doing is covering this whole quadrant of your R2. And remember when we had our negative A1 but our positive R2, what we get is something in this quadrant over here. We got this point over here. So the negative A1, the positive R2 will give you everything in the second quadrant of R2. And now you can imagine scaling V1 with something negative, scaling V2 with something negative. You're going to get the third quadrant. And then scaling V1 positive, but V2 negative, you'll get the fourth quadrant. So with all possible scalars here, all possible negative and positive, as well as fractions and whole numbers, you're going to get the entire plane. So the span of two vectors will be a plane. And that's all I have for this video. I hope it was helpful. Thank you for watching.